Once again, hello everyone, and welcome to AP Calculus BC Live. As you can tell, the chimes indicate that it is 9 a.m. this morning, and it's a pleasure to be here with you once again, whether you're watching live or on demand. We certainly hope that you had a great weekend and that you and your families were safe and healthy, and that you're ready for another week of some great AP Calculus BC content with Brian and I for the week. So, as you can see, the topic for the session this morning is defining convergent and divergent series, which really serves as the introductory concept to this final unit in the College Board Curriculum Guide, Unit 10. And it's quite possible that some of you may have been exposed to this idea prior to your school's closing, but it's also very likely that this is something that could be completely new to you. So for that reason, we're going to kind of slow this down a little bit. We're going to break it apart. And my goal today is to kind of demonstrate a practical usage for the infinite series and then sort of kind of develop that into a more conceptual understanding. Although this particular topic specifically isn't going to be tested on this year's advanced placement exam, you will find out that it does lay the foundation for 5 other topics from Unit 10 that will be tested, and we will certainly be taking a very close look at those over the next couple of weeks. Once again, if you want access to the materials that accompany any of our videos, it's still not too late if you want to try to print this out really quickly, because I've got a few other housekeeping things to address. But if you just simply go to the description in any one of our videos, you can see, like from this video, this screenshot is from Friday, but every single one of the videos has the helpful URL link there at the bottom, and you can just click that. Isaac Newton will share a folder with you, and in that folder you can see the list of all the different dates and topics, and you can download that PDF. Once again, my name is Tony Record, and I'm the calculus teacher, or one of the calculus teachers, I should say, at Avon High School in Avon, Indiana. And the students at my school are on spring break. In fact, we have a 2-week spring break, so they're right at the halfway point of that. We were doing e-learning for a long time. I think we were the first school in the state of Indiana to begin our e-learning instruction. And I was kind of missing my students, so I reached out to them over the weekend just to kind of check on them, make sure that they were doing okay. Many of them have been watching. Some of them are watching now. Thanks, guys. It's great to have your support. And we got on the subject of this whole idea of YouTube Live and what this experience is like, and the idea that you as students, and in some cases as teachers, really don't know Brian and I very well. You've seen us through a couple of sessions. Hopefully you'll get to know us more and more as we move through these 28 lessons. But they said, they probably ought to know some things about you. And I thought, well, what? Why is that important? So I did ask, I did ask, well, if you were going to share something about me, what is it that you would share? And one of them wanted to make sure that I conveyed to you, and I'm going to read this. We sincerely apologize to everyone watching about Mr. Record's lame jokes, but after a while, you tend to get used to them, or you just find a way to block them out altogether. Regardless, we still love him nonetheless. Okay, thanks, guys. And then the second and final one here is it's kind of a poignant one. It says, while we are all social distancing, I love seeing students that I consider my peers from far and wide working hard on Calculus BC instead of letting this situation get in our way. I want to wish everyone out there the best of luck in preparation for your AP Calculus exam. So that's kind of nice. Nice sentiments from my students to you. So if we look at some of our upcoming lessons, you've got the week planned out ahead of you. And as I said, today we're going to define convergent and divergent infinite series. Tomorrow, Brian's going to come on and talk about the alternating series test and getting into all the nuances that are associated with series that do have alternating signs. And then throughout the rest of the week, we'll follow up with a harmonic series and p-series, the comparison tests, and working with geometric series to end the week on Friday. And then jumping ahead to the week after, you can see that we're going to focus a little bit upon convergence of power series and really the all things Taylor polynomial, those Taylor polynomial approximations that play a critical role in Calculus BC. And then we'll end with the alternating series bound next Friday, and then that will take us right into our 3 weeks of solid AP Calculus BC exam prep, particularly geared towards this particular year's exam and its nuances. Once again, anything that's marked with an asterisk means that it is going to be tested on the 2020 AP exam. All right, so with that, let's go ahead and take a look at this wonderful warm-up that Brian presented to you guys on Friday. I believe it was about an unfortunate little bug that was walking around on a glass window. So it says, for time between 0 and 8, a bug is walking against glass doors following the path sketched, in this case, to the right. The position of the bug at time t is modeled by x of t, y of t, where y of t is t squared over 10 plus 1, and dx over dt is -5 sine of t. At time t equals 0, the bug is at position 11, 1. And you were asked to find 3 different things. The first thing is the horizontal movement of the bug to the left or the right at time 5 pi over 6, and explain your answer. And in part B, find the position of the bug at time t equal pi. And then finally, at time t equal 8, the bug gets knocked off the glass and falls into the grooves into the door track on the ground. The bug continues to walk along the ground while stuck in the door track. For time greater than 8, x prime of t, y prime of t is the position 40 over t squared, comma 0, or I should say is the velocity vector, 40 over t squared, comma 0. Write but do not solve an equation involving an integral expression that gives the time c when the total distance the bug walks after falling to the ground is 5. So perhaps you had a chance to take a look at this over the weekend. We're going to go ahead and break it down and solve it for you. So first of all, for part A, is the horizontal movement of the bug to the left or the right at time 5 pi over 6? Explain. Well, because we're talking about this idea of horizontal movement and the idea of left and right, we have to tie this to that velocity of the x position, right? We're looking at the derivative of x to determine left movement or right movement. So fortunately for us, we have the derivative of x already provided in the stem of the problem. That is our dx dt. And all that we have to do is figure out exactly what sign we've got here at the time 5 pi over 6. Now there's a lot of different ways that you can use to denote that, this just being one of them. So if I go into this dx dt, and if I replace the t with 5 pi over 6, I would have something that looks like this. And then we just have to have a pretty good understanding about what this sign is. Now I'm going to probably take this a little farther. I'd like to find out exactly what this value is. It would be good practice for us. Sine of 5 pi over 6, we think about that a little bit. And there's so many different ways that you can pull off this trigonometry. One way you could think of 5 pi over 6 is in the which quadrant here as you go around? Well, it is in the second quadrant, right? Which pretty much tells you that it's going to be a positive value, right? But if you want to get that exact value, you could extend this a little bit and say, okay, well, really what I've got right here is an angle, a reference angle that's pi over 6 degrees, 30 degrees, or pi over 6 radians rather, 30 degrees. And then that could relate to the fact that the opposite side could be 1, the hypotenuse would be 2. I'm not using a unit circle here, obviously, but we could see that that's going to be positive half. Sometimes it's nice to have that little trig refresher course every now and then, even in BC Calculus. So we end up with -5 halves. But again, what we're a little bit more concerned with here is the fact that we have a negative value. And when we have a negative value, we know that our motion is going to go to is going to be going in the left direction. So it does want us to explain that a little bit. So we'll just simply say this bug is moving left. At time equal 5 pi over 6. And the reason, you can certainly use abbreviations like that on the AP exam, because, and I'll just reiterate the fact that dx dt, what we just found here, was a negative value at t equal 5 pi over 6. All right, so if we move on to part B then, we're asked to investigate the position of the bug at time t equal pi. Now, because we're dealing with position that involves two fronts here, we need both a horizontal and a vertical component, right? We're dealing with vectors here. We have two things that we have to find. We have to find a y value at time pi, and we have to find an x value at time pi. Well, fortunately, the y value at time pi, which I'm going to actually find first, is going to be a little easier here because we can see that we've got this y equation already presented to us in the stem. So all that we need to do is replace the t with pi. We would have pi squared over 10 plus 1. And really, that's about all that we can do with that without the use of a calculator. We'll find out here in just a moment that pi squared over 10 is very close to 1. In fact, pi squared, 3.14159 squared, is very, very close to 10. And so this is probably a value that's somewhat in the neighborhood of 2 when all is said and done. But for the x component, because we are given a derivative of x, we're going to have to essentially undo that derivative. We're going to have to integrate, take the integral of that -5 sine of t, and we will do so with respect to t. And because one of our times, or the time that we're trying to find, is pi, and the fact that we were given an initial position at time 0, it seems very, very logical that 0 and pi should be our boundaries of integration, right? At one of the boundaries, we have information. At the other boundary, we're looking for an answer. So once we have this set up, we know that we can come up with our result, and that would be, well, we're integrating essentially a dx dt. Maybe I should kind of emphasize that that's what that expression really is right there. And that's going to give us an x of pi minus x of 0. Now, this isn't necessarily the way that I show this to my students. I like to illustrate the fact that when we talk about accumulation, this is a situation where we can say that we're really starting with some kind of an initial amount at x0, right? So if I were to add that over to the other side, and then I could add this integration. Once again, -5 sine of t dt. That is going to equal our x of pi that we're trying to find. Okay, it doesn't really matter really how you're going to set it up. You're going to get the same answer for x of pi either way. So if I take the antiderivative of -5 sine of t, what that gives me is a +5 cosine of t. We have to think there for a moment that the antiderivative of sine is negative cosine. And it's going to wipe out that negative that was at the beginning. And we are going to evaluate this, upper boundary of pi, lower boundary of 0. And again, that's going to equal x of pi. And I tell you what, let's go ahead and do what I did down here below. Let's put that x of 0 in front here. All right, so the x of 0 we know was 11, right? That was in the stem of the problem, the initial position, 11. And if we evaluate what we've got here, 5 cosine of pi, well, 5 cosine of pi is -1. And then we subtract, and then we have 5 cosine of 0. Well, the cosine of 0 is +1. So we have something along those lines. And by the time we do a little simplifying with this, 11 minus 10 is 1. And that is our value for x of pi. Okay, now we certainly have the two components of the position on our page, but it would be nice if we could sort of tie those together a little bit and put them in this nice ordered pair. So our final answer would be the ordered pair 1 comma pi squared over 10 plus 1. Now, before I move on to part C, I'd like to just really quickly do something kind of similar to that I did on Thursday and just give you some visual representation of what's going on with this particular problem. So if we take a look one more time at the graph that I'm going to make here, and this is going to look a little bit like the graph that you saw on the window, a little bit more dynamic, but I am going to go ahead and put this in motion, but I want to kind of set this up for part A at 5 pi over 6. I want to try to stop this motion and see what's happening. And I went ahead and worked 5 pi over 6 out before the video and got about 2.6 as a decimal approximation. So if I can set this in motion, I'm going to try to stop this when the time right here is 2.6. Let's see if I can do that. Oh, this is pressure. Hey, I got it done. All right. So that's what our particle, that's what our bug is doing right there at time 5 pi over 6. And we can see he's been moving to the left this whole instance, which reassures what result that we've got. Now, in part B, we were finding the position of the bug, right, at time t equal pi. So I'm going to set this in motion just a little bit longer. Now, I don't want to go too far with it because I'm pretty close to time being pi right now. Now, because my increments is set in tenths, I didn't want to keep you guys here all morning watching this bug moving along this graph. Because this is incremented in tenths, I'm going to probably have to stop this at 3.1 and call that close enough. So let's see if we can start it again and stop it at 3.1. Well, okay, that was a fail, but you know what? 3.2 is pretty close, right? It's in that ballpark. But as you can see, that position of that bug is indeed going to have an X value. Looks like it's 1, and that Y value, remember, is going to be something pretty close to 2. That's that pi squared over 10 plus 1. And if we kept moving this along, this thing is going to look exactly like the graph that Brian presented to you on Friday outside that window. All right. Okay. Hate to spoil the end of the movie, but let's go on to the next problem here. So for part C, at time t equal 8, this poor bug having a bad day, he gets knocked off the glass and he falls into the grooves into the door track on the ground. And then he continues to walk along the ground while he's stuck in that door track. For time t greater than 8, x prime of t, y prime of t is 40 over t squared comma 0. We're going to write but do not solve an integral, an equation involving an integral that gives the time c when the total distance of the bug that he walks after falling is going to be 5. So let me see if I can create a little bit more space here. And we'll think about this here. So this goes right hand in hand with one of our lessons yesterday. It's really the length of a curve in parametric. When you're talking about the total distance that we're traveling in parametric, we can use that particular equation. Now that equation is something that won't be tested on this year's exam. It's good calculus nonetheless. But if you recall, it's that equation that says that your distance or your arc length is simply the integration with some boundaries of the square root of your x prime squared plus your y prime squared. Okay, again, that was something that was discussed last week, and it actually showed up both in video number 2 from section or topic 9.3, and then Brian elaborated on it even more on Friday's video in topic 9.6. So our x prime of t, you can see, has already been taken for us. So we don't have to work very hard to find that. That's 40 over t squared. But remember that we must square that. And then we'll add to that. And then the y prime of t, 0, and we will square him. And we will extend our square root. We're going to integrate with respect to t, and then we got to throw our boundaries in here. And you got to think a little bit about this. It would be very easy just to want to start our integration at the boundary of 0, but we have to remember we're not focusing on distance traveled when when the bug was on the glass, but when the bug had fallen into the door track. So that doesn't happen until time 8, right? The bug fell, he's kind of composing himself, however bugs would compose themselves, and he's going to decide to kind of continue to walk. And we don't know at what time he's going to stop walking, so we call that C, but we know that this is all going to have to equal 5, right? And for all intents and purposes, that takes care of the directive of the problem. I'm going to go ahead and simplify this just a little bit, but it does say that we do not have to solve this yet. We're going to take another look at this here in a moment. But If we just clean this up just a wee bit, we find out that the square root and the square attached to this 40 over t just will cancel each other out, essentially. And you're left with this. And I'll tell you what, I'll just put the 5 over here for the distance, and that would be an integral that potentially could be solved, and we could find this value of c. All right. So if we look on forward to our lesson overview, what are we actually going to do today is, well, I'm going to introduce this concept of an infinite series to you. And in conjunction with that, we're going to determine whether these series will converge or diverge. We're just going to start to lay the groundwork for that. There's a plethora of tests that some of you may have already learned. Some of you are about to see them over the next few days. Maybe some of you are working with them now with your teachers in e-learning that are associated with being able to determine whether series converge or diverge. And then we'll talk later on, well, why is it even important to discuss whether these series converge or diverge? As far as some of the things that you should already know, you're going to be exposed to some summation notation a little bit today. So we're going to be dealing with that quite a bit. And of course, the techniques for evaluating limits are going to be very important, especially using L'Hopital's rule from time to time. An example of what you might be able to do after today or the next maybe video or two is answer some practical questions like this. Say if you have a ball that's dropped from a height of 12 meters, each time it strikes the ground, it bounces back to a height of 3/4 the distance from which it fell. The question could be, what is the total distance that the ball travels? And I know that sometimes these what we'll be able to do questions we feature here, we don't really end up solving, but I know that a lot of you from some of the feedback that we've been giving are solving them anyway, and that's absolutely fantastic. But it's a great problem if you want to take a look at it. All right, now, you'll notice at the very outset of the guided practice, we're going to revisit the answer from today's warm-up. That equation that involved the integral expression that gives the time t when the total distance that the bug walks after falling to the ground is 5. Let's go ahead and solve this for c and maybe talk about how this connects to some of the other ideas. So if we were going to go ahead and solve this, it doesn't look like it's too terribly difficult of an integration problem to take care of. What you want to be careful of, though, is you don't want to assume that this is a natural log form. Hey, just because we have this variable in the denominator, right? Doesn't matter what power it's raised to, we always use the natural log. If you're a teacher watching this, you know what we're talking about. We've seen students do that from time to time. But let's make sure we understand that that is a t squared. So if this was having a dream, right? If we were dreaming here, this 4 over t squared is really 4t to the negative 2. So now if we integrate that, we would end up with 40t to the negative 2. So we'd have 40 t to the negative 1 power over negative 1, let's say, right? And then our boundaries of integration are still going to be upper boundary of c, lower boundary of 8. And we know that this is going to be equivalent to 5. Okay, well, the problem says solve for c, so we'll go ahead and do that. And we end up with negative 40 over t from c to 8. And we plug in our c for the value of t, subtract. We do the same thing and plug in our 8 for t. All right, and then I'm going to kind of work up here in this next column so I don't have to scroll down. And we have negative 40 over c. Let's see, this is a plus 5 equal 5. Okay, so it looks like those 5s are going to go away. So negative 40 over c is equal to 0. And then we start scratching our head and thinking, okay, well, what's the value of c here? We can't cross multiply, right? It's very easy to think that this problem has no solution, maybe outside of a calculus course, that's what we would say, but there are a lot of other ways that we can think about it now that we have this power of calculus, the power of the limit, the power of the infinitesimal, the power of infinity. So we can look at this and think, okay, well, wait a minute. If you have a fraction that's going to have a value of 0 when the numerator certainly can't be 0, the only way that that can even happen is if the c value was getting awfully close to a very, very large number like infinity. And now maybe that starts to make a little sense. Oh yeah, negative 40 over infinity would approach 0. But we have to think about what this is really saying here. We're saying that the time that this bug would have to walk along that door track to achieve a total distance traveled of 5 would have to be infinity. Poor bug. He's going to have to walk the rest of his life. And then we have to address the question, does he really ever reach that total distance traveled of 5? Or does he just approach to it? Or maybe does he converge to that total distance traveled of 5? So it's probably acceptable in this particular situation to say that the limit as c approaches infinity of this quantity is indeed 5. And there's a tie-in that this problem has to some of the things that we're going to talk about. And I think this speaks highly to the fact that my partner, Brian Passwater, is probably the greatest problem writer I've ever met in my entire life. This is a completely original problem that he put together just a few days ago that ties some of the ideas from what we were doing in Unit 9 here as a great introduction to what we're going to get to in Unit 10. So we definitely thank Brian for being able to do those wonderful things. Oh, thanks. I got a little carried away here. As c approaches infinity, I'm sorry, that limit is going to be 0. I got confused. The 5 is the distance that we were traveling, but this actual limit is going to be 0, right? Just kind of getting back to this equation that we had up there. So apologize for that. All right, let's move on to our practical use for this. And I tell you, this is going to be kind of interesting here. I wanted to develop a way to really give you an idea about what is the practical application of an infinite series. And I thought about, in front of you today, actually taking a piece of food, a donut, a pizza, or whatever, and then cutting it in front of you and showing you how that can all relate. But for one thing, that would take an incredibly long period of time. And I'm not real keen about using a knife on YouTube Live because accidents happen. This could end up being a very short video because of that. So what I did is I kind of filmed what that particular demonstration would look like. And I'm going to go ahead and show this to you right now. It's going to go kind of fast because I have it in time-lapse mode, but we'll talk about it here in just a little bit. But this should set up what we're going to be doing the rest of the time.
Hi everyone, Mr. Record here, a math teacher from Avon High School in Avon, Indiana. And I just got to thinking about something on this Saturday afternoon. I got to thinking about infinite series and the fact that we can add a seemingly infinite number of terms and reach a finite result. So I got to thinking more and I thought, well, what better place to illustrate this crazy math phenomenon than right here in my own kitchen? So let's check it out.
Now, as you can see here, we're going to be dividing a pizza among 3 students, Alicia, Ben, and Carlos. And there's always going to be a piece that's left over. And we're going to kind of break this down a little bit. But yep, you can see that trying to divide those leftover pieces into fourths over and over again, it was kind of challenging, but it was leaving very little pizza left behind. So as I said before, we're going to kind of break this down a little bit because I know that video went pretty quickly. And this is outlined also in the handout, if you haven't had a chance to download it yet. But basically our situation here in example 2 is that we have 3 AP Calculus students, Alicia, Ben, and Carlos, and they're going to take a much needed break from studying for their AP exam, and they're going to split a pizza. However, they approach the division of their pizza in a very interesting way. So we initially start by dividing it into fourths, right? We want everybody to have a very fair slice of the pizza, but yep, we only have 3 students. So we have this leftover slice right here, right? That's kind of illustrated there in the picture. And the question in our first recap is, well, how much of the pizza would each student have on their plate after the first cut is made? Well, it's pretty clear that each student would have a fourth, right? And then this leftover slice would be a fourth of the pizza. Well, if I move on to the next cut, I took that fourth, and as you can see up here in this picture that I'm outlining, I cut that fourth into additional fourths, and I'm going to redistribute those. And what happens is I put one of these extra sections on everybody's plate, which leaves this extra leftover piece here. Well, we have to kind of consider, well, how much of the pizza is each of these new fourths? And the answer to that would be a 16th. So if we recap and ask, well, how much of the pizza does each student have on their plate now? We would see that Alicia has, well, originally she had the 1/4, of course. And to that, we're going to add a 1/16th, right? And if we want to go ahead and simplify that, and I think we probably should, it's going to make some things a little bit easier for us to discuss later. We're going to get 4/16 and 1/16, which is 5/16. And I really don't see any need to rewrite that same expression for Ben and Carlos. It's going to be the same amount. Each of those two students has 5/16, and then our leftover is still going to be the 1/16. Well, we just keep it going. We're going to take this 16th, and now I'm going to divide this into 4 other equal portions. And if I put each of these on somebody's plate, let's see if I can use a color that shows up a little bit, put each of these on somebody's plate. And then I have another leftover piece that hopefully we can all understand is, give you a moment here to think about it, would be how much of the original pizza? And the answer is 1/64. So at this point, how much of the pizza does each student have on their plate after the third cut is made? Well, remember, Alicia and her friends at the very outset of the cut 1 had 5/16, right? That was the 2 original pieces. And then we're now going to add a 1/64 of the pizza. And if we do our common denominator work, 5/16 is 20/64. We end up with 21/64 for each of the 3 students. And that leftover piece is going to be a 1/64. It's getting smaller and smaller. It's also getting harder to cut, trust me. So if we move on to the next and final cut, that 64th somehow got cut into 4 very, very, very small pieces of pizza, and they were distributed among the 3 students again, just kind of stacking them with the other slices that they had. And that leaves us with this teeny morsel of a slice of pizza left that would account for how much? Well, 1/4 of a 64th would be 1/256. So basically, if you could eat 256 slices of pizza that big, you would have eaten the entire pizza, I suppose. So we look at how much of the pizza does each student have now? Well, remember, Alicia, Ben, and Carlos from the previous cut had 21/64, I believe. And if we add 1/256, and if again, you get the common denominator multiplying by 4, 21 times 4 is 84. And then if you add 1, you're going to get 85/256. And I think we're all glad that we're not going to slice this pizza anymore. Trust me, my fingers were glad as well. So we know that each of the 3 students are going to walk away with this much. Now, we still have this leftover slice of 1/256. Now, if you think about continuing to cut this little guy, after a while, it's probably going to be very hard to see that there's any pizza left. But there would be these very small, infinitesimally small slices going to each of the 3 students. Well, that kind of brings up the ultimate question here. How much of the pizza will each student actually receive? Well, it seems like they've all 3 have acquired the combined total pizza among them, and they've done so evenly. It only stands to reason that each student would have received 1/3 of the pizza. But the interesting idea is that we were only dividing it into fourths the whole time. And kind of to move from the practical to the conceptual here, those fractional slices of pizza that we talked about, that would be the 1/4, the 1/16, the 1/64, they're called the terms of the series. And then each student's fractional amount of pizza after each cut, that would be that combined accumulation, that 1/4, and then that 5/16, and then that 21/64, and I think 85 over 256. Those are going to be referred to as what our partial sums are. And because the total fractional amount of pizza each student is receiving is approaching 1/3, we can say that the limit of the partial sums, or the limit of the series, is 1/3. Okay. Now we could do something very similar with another type of food item, and I experimented with this as well. So this time I've got a chocolate cake that I bought, baked, to be evenly divided among 4 students, Alvin, Bianca, Celeste, and DeAndre, by continually dividing it into 5 equal pieces. All right, now I'm not going to walk through the whole process here because I think you kind of understand what's happening, but you can see from the picture I have 4 equal slices for those 4 students, and then on the right is the leftover. And I could ask, well, what would be, they say, the first 4 terms and a general term of a series that would model the amount of the cake that each student would receive after each cut? Well, from the very outset, we can see that each student would have received 1/5 of the cake from the beginning. And then from the picture down below, you can start seeing me stacking other slices of the cake, other terms in the sequence. And I think the one that I circled there in blue is actually going to be the next slice, which would be 1/5 of the 5th, which in this case is 1/25. And then I'm going to move to a red pen, and that's up here. You can see that I had the additional 1/5 of the 1/25th slice that I added to each student. And then if I move down here to the bottom, I think that's the next slice when I took that 1/25th and divide that into fifths, which in this case is 1/625. And because the numbers are starting to get pretty rough, I'm not going to go up to the guy, that little teeny tiny piece at the top, but I'm going to say, well, we could go ahead and just add this infinitely until we get to some general term. And that general term, you can see, is just simply a fraction, right? Where the denominator is changing, but the numerator is, of course, 1. And that denominator is changing in such a way that we have a base of 5 because we're dividing it into 5 pieces, but we're just going to use an exponent to indicate the sort of the sequencing of how we are dividing this particular slice of cake. And we could actually find the sum by using some techniques that both Brian and I are going to talk about later in the week. But for right now, we can think about this very logically, very practical. There were 4 students that were dividing this cake, and they all got an equal portion. So how much of the total cake will they receive? Well, we hope it's 1/4, right? Because I'd be pretty mad if I didn't get an equal portion of the cake, right, with my friends. Now, the actual definition of convergence divergence is outlined in this box. And we can talk about it as kind of relating to the sequence of partial sums, which I'll call S sub n. And the summation A sub n would have a limit S. If it has a limit of S, then that series is known to converge, and it's said to have the sum S. So to put it kind of simply, if the limit of partial sums as n approaches infinity is equal to some finite value S, then it turns out that that S is the sum of our infinite series. Now, a few things that you have to be very careful of. Let's say that the limit of those partial sums approaches infinity or negative infinity. Then we know that that particular series is going to diverge. Or maybe it's likely that that limit of those partial sums doesn't exist for some other reason. Then we're going to also diverge as well. So this idea of divergence is going to come to fruition in a lot of our lessons this week. And I wanted to kind of throw in this idea because we don't have a specific lesson devoted to this, the nth term test for divergence. It's probably one of the easier tests to apply. It's one of the earlier tests that you might want to think about using. And it just simply says this, that if you have an infinite series, summation of A sub n as n goes from 1 to infinity, we know that that's going to diverge if the limit of the nth term expression as n approaches infinity is not equal to 0. Now there's a caveat to this. We can't work in reverse and assume that this is going to be true if we negate everything. We can't say that, oh, well, does that mean if the limit is equal to 0, that we converge? And that's not necessarily true. In fact, no information about convergence or divergence can be obtained. It might converge, but it still might diverge. So I've got just a couple of really quick problems that shouldn't take very long here for you to practice with the nth term test for divergence. And I'd like to set the timer here just to maybe 1 minute and have you kind of look through these while I take a sip of water, and we'll go through these solutions here. So see if you can use the nth term test for divergence and find out some information about these guys. Okay. Now I know that was pretty quick. Working each one of these at a 15-second pace is a pretty tall order, but let's see how you were able to at least get through the first few. And I'll start by taking the limit as n approaches infinity of this expression, n over 2n plus 1. And we could use a variety of ways to solve this limit. Probably my favorite, because we have our n approaching infinity, we could compare the degree of the value of n on the top and on the bottom, and they both have exponents of 1. They match. So that basically says is that we could divide by the coefficients. And this limit is going to be 1/2. We could also use L'Hopital's rule pretty quickly there. Now, because this limit is not equal to 0, right? Last time I checked, 1/2 is not equal to 0, then we know that this is going to be a divergent series, right? If the limit is not 0, we know that we diverge. Now, if you take a look at 2, and I'll tell you what, I'm going to maybe think about 3 in the same light. They have very similar characteristics. In both cases, if we let n get as large as it wants to be, that's going to cause the denominators to get very large, right? Now in problem 3, the denominator is going to get larger faster. We kind of think, well, does that make a difference? Does that mean something? Down the road, it very well might. But in the case of this nth term test, we can see that both of these limits are going to be 0, which means that the nth term test doesn't apply. All right, and I think what I'll just do for purposes is just say not applicable in A. Okay, now we still might diverge, we still might converge, and some of you might know the answer to these because you've been exposed to it, but if you haven't been exposed to this, this is something that's going to be coming to you this week. In fact, one of those converges, one of those actually diverges. All right, now if you look at the last one here, for the limit of the natural log of n over n, this one's going to take a little bit more thinking because we have the issue of an indeterminate form. If we try to let n grow really fast, we get an infinity on top of an infinity. So that means that we're going to have to use L'Hopital's rule. Now, in the interest of time, I'm going to go ahead and just use L'Hopital's rule right from the very get-go. But whenever we use L'Hopital's rule in a free response format, it should be very important to us that we talk about the conditions of L'Hopital's rule. So we should probably say that the limit of this numerator as n approaches infinity is going to approach infinity, and the limit of this denominator as n approaches infinity is going to approach infinity. Therefore, L'Hopital's rule is going to apply. But for the purpose of this video, I'm just going to go ahead and perform the L'Hopital's rule very quickly. And once again, we see that, well, we're going to get a 0 for this, right? And getting 0 is the worst thing that can possibly happen if you're going to use the nth term test. It just simply says, oh, darn shucks, we're just going to have to look at using another test. And I don't want to spend a lot of time with the graphs that I've made for these particular problems, but you can see here, these are in the documentation that you can download. And I will be using these graphs again later in the week. But remember our first particular one, the nth term expression that was n over 2n plus 1 in practice 1. Well, this shows you a nice graph of the sequence of terms, right? It certainly looks like an increasing sequence, but it's kind of starting to level off a little bit. In fact, it looks like it's going to level off at 1/2, right? We're going to flatten the curve at 1/2. Well, that makes sense because we took the limit of this a moment ago to get 1/2. But we're now interested in graphing what the series would look like. All of those partial sums, if we were to take the value here, which is 1/3, and add the value here, which I believe is what, 2 over, when n is 2, you get 2 over 5, right, 0.4. And if we keep a running total of those particular items and graph, we're going to see this green curve. And it's very, very, very obvious, I hope, that this graph is just sort of going way up into the atmosphere to infinity, and that's why we could say that this diverges, right? We're not going to reach that finite value. Now, if we take a look at, well, let's take a look at that 1 over n squared, okay? Those are what the nth terms look like when we sketch. But if we were to sketch the partial sums, we don't quite get that, moving way into infinity. We sort of get this leveling off, but are we really leveling off, or are we still increasing just at a very, very slow rate? So those are going to be questions that we're going to be able to address later on through the week. So for debrief and summary here, if we kind of wrap this up and look at the enduring understanding that we're trying to convey, and it's just simply that we can see that applying limits may allow us to determine the finite sum of a group of infinitely many terms, right? It's still it's an idea that still to this day blows me away. You can add an infinite number of things and get a finite result. A couple of our key takeaways is that if we do sum the partial sums and get a finite value that we call S, then that means that that particular series will converge. And then our nth term test takeaway is that the summation of a sub n will diverge if the limit as n approaches infinity of an is not equal to 0. Common errors, misconceptions, and pitfalls. Certainly you want to know the difference between a term a sub n and a partial sum s sub n. It's very easy to get those two things confused. And then let's not forget that if the limit as n approaches infinity of a sub n does indeed equal 0, this does not necessarily mean that the series will converge. A different test may be required, and Brian and I will be talking about those throughout the week. We've got just a really short AP practice question here. It's not going to take a whole lot of your time. You could just take a look at these maybe before tomorrow, and perhaps Brian might address some of these. But it's just a way that you can maybe use this nth term test and practice just a little bit, because we know that you're a little limited on the number of tests that you might know, especially if this has been new to you, if you haven't been exposed to this before. All right. Once again, we want to make sure that all students have access to the internet. So if you have a friend that you know is having a hard time, they want to access advanced placement, the channel here on YouTube Live, have them reach out to the College Board at cb.org/tech, and they will certainly steer you in the right direction. Last Friday, Brian had a great project for you guys to tweet out with the hashtag AP Teachers Rock, AP Students Rock. It's a way that we can sort of keep our community tight and really start to celebrate some of the wonderful things that are happening, because it's tough. This is tough for teachers. This is tough for students. And we want to make sure that, that you're all understanding that we can get through this, and there are great teachers out there. There are great students out there. If you're watching this, you know that you're a great student by taking 45 minutes of your time to work on your calculus. And so a couple of featured tweets as far as the AP Teachers Rock is concerned is coming from a group of students that said, I want to give a huge shout out to my calc teacher, Mrs. P. Not only has she spent her time reviewing with us over this break, but she always asks if we need anything not related to math. She's a great teacher and a great person. And I am sure that Brian and I would agree that our students are very lucky to have her. On the side of AP Students Rock, we had a teacher to say that we are going to give a huge shout out to my AP Calculus students who are continuing to work and review all of our content, despite the fact that teachers aren't permitted to grade our activities. I'm so proud of your tenacity. You will rock the exam. So it's so great to see all these positive sentiments being sent on both sides of the classroom. Brian and I certainly believe that staying positive is of the utmost importance during this time. You know, never stop believing that you're among the best mathematicians in your schools. You're among the best high school mathematicians on this planet. If that weren't the case, you wouldn't be taking calculus BC. And you know, I'd be lying to you if I probably didn't have ulterior motives in wishing you success. You know, those of you out there watching, you're our future engineers. You're the engineers who are going to develop things that make all of our lives easier. Some of you may work in the business world. You're going to be the ones who are going to keep our economy growing for future generations, for my kids, my grandkids. Some of you may be healthcare professionals. I certainly can't say enough about how important the roles of these individuals are right now in our society as of late. And some of you, you may be scientists. Maybe you'll be working in a lab one day. Maybe you'll discover medicines, vaccines, and even cures for chronic illnesses and even infectious diseases so that we may never have to deal with a situation like this again. You know, a famous AP Calculus teacher from Bolivia who taught in California said it best. You are the true dreamers, and dreams accomplish wonderful things. So I want to thank you for watching. We know that Brian is going to come in tomorrow and give us a great lesson over alternating series. So we want to make sure that you do try to complete this practice question, and we'll be back with you tomorrow. And in the meantime, I'm going to enjoy a little slice of pizza. So enjoy your day. We'll see you next time.